welcome to the third lecture. Today we will see some examples of how to construct deterministic finite automata for certain languages. So, today we will look at more examples of DFA. So, in particular we will try to see what kind of languages that are accepted by these models of computation. So, the first language that we will see is let us call it L1, set of all strings over the alphabet 0 1. So, this is the set of all strings over 0 1 such that W has an even number of ones. Okay. So, all strings that contain an even number of ones. So, how do we construct the DFA? So, once again before constructing the DFA, let us try to understand what property the states should capture. So, if we look at all possible strings over 0 1, either they can have an even number of ones or they can have an odd number of ones. Okay, so, we will have two states, one capturing all strings that have a even number of ones and the other state capturing all strings that have an odd number of ones. So, we start with the state Q0. So, initially let us say Q0 is our start state. So, the empty string by definition does not have any ones. So, which means that it has an even number of ones. Now, if we see a single one, we go to a state Q1 which corresponds to seeing an odd number of ones. Okay, so, if we see a single one, we go to Q1, and again from Q1 if we see a 1, it means that we have seen an even number of ones, we come back to Q0. Okay. And in both these states, if we see a 0, it does not matter. I mean, we can see any number of zeros between two successive ones, and it will not affect the parity of the ones. So, if you see a 0 from Q0, we stay at Q0, and if we see a 0 from Q1, again we stay at Q1. Okay. So, to formalize, so Q0 corresponds to all strings having an even number of ones, and Q1 corresponds to all strings having an odd number of ones. Okay. So, therefore, the accept state in this case is going to be the state Q0. Okay. So, instead of even, if we had a language which consisted of all strings having a odd number of ones, our accept state would have been Q1 instead of Q0. So, now let us move on to our next example. So, let us look at a language consisting of all strings over so, let us in this case change the alphabet. So, we will take the alphabet to be the symbols A comma B. So, I look at all strings over the alphabet A B such that W ends with the substring AB. Okay. So, how do we construct an automaton for this? So, let us try to understand again what kind of information should the states capture. So, when we look at the set of strings, so when we look at the set of strings that end with an AB, I can look at the set of all strings over AB and classify them into 3 sets. So, one set can be strings that end with an AB, the other set will be set of all strings that do not end with an AB, it just ends with a single A, and the third will be all strings that do not end with an A also. Okay. So, I start at a state Q0. If I see a single A, I go to a state Q1. If I see a B after that, I go to the state Q2. So, this kind of represents the fact that I have seen a substring AB. Now, we must consider strings that end with AB. Okay. So, for example, from here from Q0, if I had seen a B, then I will stay at the state Q0 at itself. From Q1, if I see an A, I stay at Q1 itself, because Q1 corresponds to all those strings that end with an A. And from Q2, if I see a B, it means that I have, so the string ends with 2 B's, in which case I come back to Q0. And from Q2, if I see an A, it means that I have a string that does not end with an AB, but it ends only with an A, in which case I will come back to Q1. And our accept state, so firstly our start state. So, start state is going to be the state Q0, and our accept state is going to be the state Q2. Okay. So, let me write down the intuition that I mentioned about the states. So, in this thing Q2 corresponds to all strings that end with the substring AB. Q1 corresponds to all strings that end with the substring A, and Q0 corresponds to the remaining strings basically. So, basically all strings that end with B that does not have an A before it. Okay. So, it can either be BB or it can be a single B or even the empty string epsilon. Okay. So, once again in this example, what is important is when we see an AB. So, the automaton, whenever it sees an AB as the last 2 symbols of its input, no matter which state it is in, if it is in Q0, it will still move to Q2. Okay. So, if it sees AB, it moves to Q2. If it is in Q1, even then it moves to Q2. Okay. So, from Q1, if it sees an AB, it stays at A and then it moves to B. And the same thing for Q2 as well. Even from Q2, if it sees an AB, it moves to Q1 and then back to Q2. So, no matter which state the automaton is in, if it sees an AB at the end, it will move to Q2, and if it does not see an AB at the end, for any other pair that can happen, okay, it will not end at Q2. It will either stay at Q0 or it will stay at Q1. Okay. So, that ensures that the automaton that we have is correctly captures the language L2. Okay. So, our third example, so okay. We consider the language L3 that consists of strings over 0 1. So, all binary strings such that W is divisible by 3. Okay. So, if you look at the decimal equivalent of that string, it should be a number that is divisible by 3. Okay. So, once again here how do we capture this? I mean, how do we construct an automata that would accept exactly those strings, exactly those binary strings that are divisible by 3. So, first of all we have to figure out how many states do we need and what would be the intuition behind those states. Okay. So, what would be the strings that those states capture. So, we will so since we are looking at divisibility by 3, note that every string will have the property that either the string when divided by 3 leaves a remainder 0 or it leaves a remainder 1 or it leaves a remainder 2. Okay. So, every string either has one of these 3 properties. So, we will have 3 states corresponding to these 3 type of strings. So, we have Q0 which corresponds to all those strings that leave a remainder 0 when divided by 3. We will have Q1 that corresponds to all those strings that leave a remainder 1 when divided by 3, and we will have Q2 that leave a remainder 2. So, we start at the state Q0, and from Q0 if we see a single 0, okay, so if we see the string, so let us keep this as our workspace. So, what happens when we see a single 0? So, 0 is the string which when divided by 3 leaves a remainder 0, right. So, if I see a 0 or if I see any sequence of zeros, it always means that I get a remainder 0. Now, what happens if I see a 1? Okay. So, from Q0 if I see a 1, it means that the string ends with a 1, in which case it means that when divided by 3 it leaves a remainder 1. So, on 1 I go to Q1. Now, what about Q1? So, from Q1 if I see a 0, it means that I have seen the string 1 0. So, 1 0 corresponds to the decimal number 2. So, if I divide 2 by 3, it leaves a remainder 2. So, from Q1 if I see a 0, I go to Q2, and from Q1 if I see a 1, so if I after a single 1 if I see another 1, so this corresponds to the decimal number 3, which means that it is divisible by 3. So, if I see a 0, I go back to Q0. Okay. Now, let us look at Q2. So, if I am at Q2, it means that I have seen a string of the form 1 0. So, after I see 1 0, if I see a 0 after this, so this corresponds to the decimal number 4. Okay. So, which means that from Q2, if I see a 0, I should go to Q1, because 4 when divided by 3 leaves remainder 0, and from 1 0 if I see a 1, it means, so this corresponds to the decimal number 5, hence I stay at Q2, because 5 when divided by 3 leaves remainder 2. So, what is our accept state? So, accept state in this case will be the state Q0. Okay. So, once again Q0 is all strings W such that W mod 3 gives remainder 0. Q1 corresponds to all strings W such that W mod 3 gives remainder 1, and Q2 corresponds to all those strings that leave a remainder 2 when divided by 3. Okay. So, similarly you can actually construct automaton that accepts strings that are divisible by 4, 5 or any other number. Okay. That is in fact a good exercise to look at, to try and construct automata for divisibility by other higher numbers. Okay, so now let us move on to the last example that I want to discuss today. So, L4 is the, let us say, the set of all strings that W over 0 1 star such that W begins and ends with the same symbol. Okay. So, I want to look at all those strings whose first and last symbol are the same. So, how do we go about constructing an automata for the language L4? So, again before I begin, let us try to understand the language L4. So, let us try to partition the set of strings that the set of all strings over 0 1 star into some sets and try to understand them. So, I can write the set of all strings as follows. So, strings that begin with 0 and end with 0. Then I can have set of strings that begin with a 0 and it ends with a 1. The third is set of all strings that begins with a 1 and ends with a 0. And lastly, I have set of strings that begins and ends with a 1. Okay. So, these are the 4 possibilities that can happen if I look at the first and the last bit of any string. So, now using this idea we will construct our automaton. So, we start at some state Q0 and the moment we see the first bit of the string, we go in 2 different directions corresponding to either beginning with a 0 or the string begins with a 1. So, if the string begins with a 0, I go to state Q1, let us say, and if the string begins with a 1, I go to state Q2. And now from Q1, if I see a 1, I go to Q3, and if I see a 0, then I stay at Q1. Okay, so Q1 corresponds to all those strings that begins with a 0 and it ends with a 0. From Q3, if I see a 1, then I will stay at Q3 itself, and if I see a 0, then I go back to Q1, because this means that the last symbol that I have seen is a 0, and I do a similar thing at Q2 as well. From Q2, if I see a 1, I stay at Q2. If I see a 0, I go to a state, let us call it Q4. At Q4, if I see a 0, I stay at Q4, and if I see a 1, I go to the state Q2. Okay. So, now I can just replace this. I mean, I can say the following, that these 4 type of strings, or these 4 classes of strings that we have, can be corresponds to the following states. So, strings that begin with a 0 and end with a 0 correspond to the state Q1. Okay. Strings that begins with a 0 but ends with a 1 corresponds to which state? So, it corresponds to the state Q3. Now, strings that begin with a 1 and ends with a 0 corresponds to the state Q4 here, and strings that begin with a 1 and end with a 1 corresponds to the state Q2. Okay. And lastly, for the empty string, the string that we get without reading any symbol, so that is the state Q0. Okay. So, Q0 in this case corresponds to only the empty string. So, this is our start state, and the accept states are going to be the states Q1 and the state Q2. Okay. So, this is an automata where we have 2 accept states. So, in fact, this is the first automata where we have the first example that we have seen, where we have more than 1 accept state. Okay. So, now let us look at some important observations about deterministic finite automata. So, the first point that I want to make is that for a language there can be many DFAs accepting it. Okay. In fact, there can be infinitely many languages. For the same language, you can have infinitely many DFAs that accept the same language, but on the other direction, once if you fix a DFA, then each DFA accepts exactly one language. So, that is why when we talk of a DFA M, it makes sense to talk of the language corresponding to the DFA M. Okay. So, and we have seen it earlier that it is denoted by the notation L of M. Okay. So, this is an important point, but if we talk about a language, we cannot talk about just the DFA that accepts that language, because as I said there can be infinitely many. So, you have to specify which DFA are we talking about? Okay. So, this is the same as so in the terminology of writing computer programs, this kind of corresponds to the following fact that if you are trying to solve a certain computational problem, for example, given an array of numbers, let us say we want to sort the numbers. Okay. So, then there can be many different programs that you can write to sort those numbers. It is not necessary that there is only one particular algorithm or one computer program that is able to perform the sorting operation. Okay. In fact, if there is a class of students, each student can have his or her own computer program to perform the sorting function. So, the second point that I want to make is that, so given a pair of the form, let us say q comma a, okay, where q is a state and a is a symbol. So, from a given q comma a pair, by the definition of the transition function, so the way we defined the transition function for a DFA, there is a unique state q prime that the automaton goes to. Okay. So, from a state comma symbol pair, the automaton goes to always a unique state. Okay. For example, in the last example that we had earlier, if we look at the state q1 and we look at the symbol 0, then from q1 comma 0, from the pair q1 comma 0, we go to the state q1. Similarly, from the pair q1 comma 1, we go to the state q3, okay. And that is actually true for all the states and symbol pair in this example. So, that is the point. So, if we fix a state and if we fix a symbol, then we go to a unique state from it, and this is the reason why we have the word deterministic in the description of this computational model. So, deterministic refers to the fact that given a state comma symbol pair, the model deterministically goes to a unique state. Okay. And the last point that I want to make is that the set of states in a DFA partitions the set of all strings. Okay. So, in other words, what I mean here is that if you pick any string from the set of all possible strings, okay, you take, so suppose if you have an alphabet sigma and you take any string from sigma star and you feed the string to the DFA, then because of this deterministic property of the DFA, there will be a unique state that you will end up at. Okay. And this happens basically for all strings. So, for every string you always end up at a unique state when starting from the start state. Okay. So, we can think of the set of all strings as being partitioned corresponding to the set of states of the DFA. Okay. So, each state basically corresponds to all those strings that end up at that particular state. Okay. And we know that the set of states is finite, and this basically means that whenever we are reading any input string, we can only remember a finite amount of information, because at any point of our so whenever we are reading a string, at any point of the computation, okay, we are at one of the given states, and from that point onward whatever happens for the remaining part of the string is independent of whatever we had seen earlier, because there is no way in which we can store that information. So, the only information that we have with us is what is the current state at which the DFA is right now. Okay. So, whatever action that the DFA takes henceforth only depends on that current state, and because there are only a finite number of states, so therefore, the amount of information that can be captured by a DFA is a finite amount of information. It cannot remember information which is a function of, let us say, the input length. Okay. So, this is the reason why we again have the term finite in the terminology of a DFA.